Michael, orchestra. Sorry, bro. Michael, you did orchestra with me, dude. Yeah, don't you can't say sorry, bro, dude. You were in orchestra with me, dog, in like 5th grade, 6th grade. Um, Let me think. Actually, there's actually a cool thing with heat. We can actually we don't talk about that. We don't talk about orchestra, dude. Yeah, come on, dude. Actually, this is actually okay. This was Patty's stock advice, but okay, cool. This is actually a cool thing. Do you guys know why instruments go in and out of tune when the weather changes or when the temperature changes?
Is it like pressure or something?
No, it's not pressure. Not pressure. So, what it ends up being is that materials, right, will either expand or contract due to changes in temperature. Okay, but you guys didn't know that. Well, you thought it was the pressure, right? Yeah. So, um, the classic example of this, right, is or at least with instruments. So here's a question. Here's a good question. Here's a good question. If something heats up, do you think it expands? So does it get bigger, or do you think it contracts, gets smaller?
Expense.
Good, good. Yeah, nice, dude. Yeah,
I'm
yeah.
back.
What's up, Patty? Oh, sorry, Philip, dude. Philip, sorry. Yeah,
What's we talk?
I had a little slip there, dude. A little slip. Um,
Material expand contract. Oh,
yeah.
you know what? I watched like an hour and a half documentary about the Tom Brady
Oh,
Deflategate.
the Deflategate. Yeah.
Yeah. So there's this type of law saying since the room temperatures, like the dramatics from like the inside the locker
Uh
room
huh.
to outside where the game was able to change the PSI
Yes.
all like low enough so the balls were deflated basically.
Yes. Yeah. Exactly. Exactly. Right. Yeah. And so this is what we're getting into. So,
Right.
if things heat up, they expand. Okay. If things cool down, okay, what they're gonna do is they're going to compress. Is what they are. Okay. So, now this is cool, Philip, because this actually plays a part into. So we can we can figure out like what the Deflategate thing was, right? Deflategate. Okay. So, this is actually this is actually a little bit of what we call like thermodynamics. Does anyone have any idea what thermodynamics probably goes over?
Science.
Science. He's like science. You're right.
Thermodynamics, something about temperature and how it works.
Good, good, very good. Uh, Waiting for Geo to put in the one caveat he always loves when talking about this concept. what? What's the one caveat I always love? Oh, hot air? Is this a hot air joke? Is this I'm full of hot air? I don't know. Caveat. I'll have to. I don't remember the one. Oh, water. Yes, yes. Okay, okay. Yeah. That's a good one. Yeah, we'll go. I'll go into that. I do love talking about that. Okay, yeah. So, you're right. So science, right? And then I think Bond said the right thing. The dynamics of thermals, right? Yeah. Literally, it's in the word is what it is. This is really the study of like heat is what it is. Heat changing. Thermals, heat, whatever, and dynamics. Dynamics means changing. Okay, so heat changes. That's really all thermo is. It's just it's the study of like stuff as it changes in terms of temperatures and heats. Um, Too many biddies in my memory. There are too many biddies, dude. I met way too many biddies last night, honestly. Okay, so what we're gonna look at real quick here is what we call the ideal gas law. Okay. The ideal gas law relates different properties of a gas and how they interact and whatnot. Okay. So the equation that you use is that P times V is equal to N times R times T. So let's um
What about
let's
V?
pardon?
What are the like
Yeah, what are the
abbreviations?
letters, right? Yeah. So let's try and guess. So what do you guys think the P is for a gas?
Particles?
Eh, close. One of these actually is the number of particles, and that's actually going to be N here. This is the number of particles. Okay.
Um,
Plasma?
pressure.
Ah, good. Pressure. Pressure. This one. Plasma. That's a good guess because I am a plasma physicist. But yes, no. This is pressure is what this is. Okay. Okay. What do you guys think the V is?
Oh, probably volume.
Yeah, good. Good.
That's like every math term is volume.
Yeah, right.
That's
Volume is always used. What do you think the T is?
T.
Yeah.
Is temperature, I guess.
Good. Very good. Very good. Yes, this one is temperature. Okay, and the last one you guys aren't going to know. This is called an ideal gas constant. This is just a constant. It's what I mean by constant. Constant is just like a number they got to put in that like makes.
Every single time.
Yeah, it's just it's a number that does not change. I think it does change based on maybe what the material is. Like you have to know, like for instance, if you're dealing with air, R is equal to something, or if you're dealing with like nitrogen, R is equal to something. This is usually what is the ideal gas constant? I always forget what this stuff is. Okay, 8.314. Yeah, that's what it is. Yeah.
I feel like I'll learn some like chemistry.
You probably did actually. No, you very much probably did. This is also they do this in chemistry. So this is equal to 8.314. Okay. So
I'm taking that next year.
Cool. Well, then this will be a good little primer for
Actually,
you.
I'm taking this year.
Oh, okay, cool. Yeah, no.
Yeah.
You're definitely gonna do stuff with this, and so, here let's do a quick little question with this one, right? So you know that P times V is equal to nRT. So a lot of times, so let's get another window in real quick. Let me find an ideal gas problem.
What is like an ideal gas condition?
Oh, good. Okay. Yeah, no, this is a very, very good question. What is an ideal gas, for instance? Okay, what is an ideal gas?
Yeah.
Okay, so an ideal gas, as the name says is a regular gas that behaves in a way that you can use this equation. And an ideal, for that to happen, it needs to be not a very heavy gas, is what it is. So
can it be a noble gas?
I don't know if you. Yes, if it's one of the light ones. So helium is an ideal gas for instance. Let me see. Ideal gas constraints.
So ideal gas has to like it can't be like low temperatures or high temperatures. It has to be like
No. Temperatures are fine. Temperatures can be whatever. The issue is the size. Is the size of the gas is what it is. And so what we mean by is it's the size of the atoms in the gas. So for instance, hydrogen gas, right?
Mm-hmm.
Is made up of little hydrogen particles, right? That are pretty small, right? Whereas, let's say you have something like xenon, for instance, like xenon gas. So xenon gas, have you guys ever seen xenon gas? I'm sure you have. Like, where do you think you see xenon gas in?
Xenon gas?
Yeah.
I have no clue.
Okay, so you ever seen those like neon lights and whatnot?
Oh, the one that glows up.
Yeah. They also use neon gas, but xenon gas is another gas they'll use sometimes for different colors. Yeah.
Isn't it like XE?
Yes, it's XE. It's XE. What is it? Here, is there a picture here of this? I need the picture of the.
Is it like an LED kind of?
LEDs are very different. LEDs work by running electricity through. Not a gas. I have to remember what it is actually. That's a good question though. But okay, here's an example of. So here, let's copy this image in real quick. Can I paste things in? There we go. Cool. Y'all see this? So these are the size of the different atoms. Okay, right? So if a gas is made out of hydrogen, right? This is how big the hydrogen atoms are. Okay. But let's say you start looking at a gas that's made out of like xenon, for instance. Do you see how this is like almost? It looks like it's like 4 times as big as this one, right? This one's like a size of, I think it says a radius of, this looks like 37. This is a radius of like 130. So xenon is much bigger, is what it is. And so what happens is when a gas is made of atoms that are very big, you start getting effects that aren't due to it just being a gas. You get effects due to like the gravity between the particles is what happens. So that's why an ideal gas needs to be small. An ideal gas assumes that that these are very small such that they don't bump into each other as often, and they don't have a gravitational like attraction to each other. Xenon gas is she's a big girl. You know, she's like, you know, I eat 3 footlongs when I go to Subway or something. You know, like and
it makes it like light, right?
no, it makes it heavy actually. Xenon gas is heavier than hydrogen gas because the particles are bigger. All gases are very light, honestly, just because because by definition, a gas means that you have atoms that are very spread apart, right? A liquid is atoms that are kind of apart, but they move together. That's right. That's why like water, like, you know, moves in places and whatnot. And then a solid is that they're very close to each other and they don't move really at all. They actually just vibrate is what they do. So gases in general are all very light. But within gases, you can have heavy gases and light gases. And for the purpose of doing the equation, we're going to do that PV equals nRT. You need to only be working with light gases. Because otherwise, these like collisions and stuff like start fucking up the equation. And like you got to start like putting like there are correction factors you can put in stuff, but it's what it is. Okay, cool. So let's see. So yeah, great question there, Philip. What is an ideal gas? Let's find a question. Okay. No, I don't want that one. Yeah, here's a good one. Here's a good one. Okay. Let's say, for instance, okay, you have the pressure and the volume is going to change. No, the volume is actually the same is what happens. Yeah, okay. Let's figure out what is the volume of a what's the volume of a football? Okay.
I think I know this.
Yeah, it says 4,800 cubic centimeters. Okay, so let's say the volume of a football.
I thought it was 50 flat. Like 5,000 flat.
5,000. This says around 4,800.
4,800.
Oh wait, sorry, that's a soccer ball. That's a soccer ball, dude. Oh, sorry, the fucking. Because football, right, in the rest of the world is soccer. Okay, one sec. Okay, or they
So
say
it should be 11 inches from tip to tip.
so.
Right?
It's an ellipse. So technically, there's an equation for this, but I just want the answer. I don't want to actually derive it.
We can figure it out.
Let's just say it's 5,000. Let's just say it's 5,000. I think I'll take that. Let's say a football. You're right. We could figure it out, honestly. Maybe we'll do that if we have time. Let's say a volume of a football is 5,000 centimeters cubed. Okay. And let's think. What was the temperature in the locker room? Do we probably think?
I think it was like 78, 76.
78, 76, right? Yeah. So temperature in the locker room. It's probably like so 78, 76 degrees. But we always need these in so there is some caveats here. Whenever we do stuff in science, are we allowed to use units like inches and like Fahrenheit?
Yeah.
No.
Why not?
Because all these equations all use what we call like the metric system is what we do for things.
Oh yeah.
Right. So even though this is 78 degrees Fahrenheit, we need to convert this into Celsius, which is going to be 25.6 degrees Celsius. And even further, actually, this needs to be converted into Kelvin. Have you guys heard about Kelvin before?
I don't know how to convert it though.
Okay. So here's what you do. How to get from okay. So whatever the temperature is in Celsius, you're going to add 273 to, and that's the degrees in Kelvin. So if this was 25.6 degrees Celsius, how many degrees is that in Kelvin?
E plus 273?
Yeah, it's 25.6. Yeah, it's whatever the degrees are in Celsius, right?
Mm-hmm.
So in this case, it would be 25.6 plus 273, right? And that is, what is that? That's 298.6, right? 298.6. 0.6 Kelvin. Yeah. Kelvin is, again, that's the unit you're going to use in chemistry. For anytime you do temperatures and stuff, you almost always want stuff in Kelvin. The reason for that is, can you see what temperature would I need to be in Celsius to be at 0 degrees Kelvin?
Negative 273.
Nice, good, yes, negative 273. So negative 273 degrees Celsius, which equals 0 degrees Kelvin. This is what they call absolute zero.
I thought it was like a term in geography or something.
Yeah. Well, what do you think absolute zero means, Philip?
In like geography?
Yeah. Well, what does it mean in geography? I guess I don't know.
I think it meant like 0 degrees latitude is like the prime meridian, I think.
Okay. Yeah, kind of like a reference point almost, right?
Yeah.
So it happens.
Or I did it in math.
Yeah.
I don't know.
So in science land, absolute zero is the lowest temperature anything can ever be. It's actually kind of cool. Do you know how we measure temperature? Like what we define temperature as being?
No.
So temperature is defined as how fast particles are moving around, like how much they're vibrating and whatnot. Yes, good, Bomby Boy. Yeah, the molecules are moving. Right. So when we measure temperature, we're really just measuring how fast, for instance, the air molecules are moving around and whatnot. And as things get hotter, the particles start moving more. They move faster. So temperature was defined by Shonda Paul. Yeah, I see the right. Okay. Someone give it to. So it's a very cool thing. At absolute zero, atoms stop moving. Like at absolute zero, which is impossible to get to. That's the temperature at which everything stops. Everything literally freezes and nothing moves. It's very cool actually, because even for instance ice, when ice is frozen, ice particles, the water inside are still moving. They're vibrating a very little bit. They're like they're stuck to each other, but they're still vibrating. If you cool it down to absolute zero, that means they won't move at all. So food for thought there. Okay, let's think. Okay, so we got a temperature. Let's see what's the pressure that you usually pump a football to?
I know it could, like, you have a choice. It's between two numbers, but I don't know what it was.
It says 0.5 to 0.7 bar is what they say. 7.2 to 10.1 psi. Okay. Okay, so let's say it's pumped up at its maximum. Well, let's say it's pumped up at.
It says NFL footballs have to be inflated between 12.5 and 13.5.
Oh, psi.
PSI. Yeah.
Okay, so PSI is another unit that we don't really like because it's like inches and pounds and
pressure per.
Yeah, it's pounds per square inch is what it is.
Pounds per square.
Okay, so when we use this equation, we got to use the metric system, which means I need what's called atmospheres. So the pressure. Yeah. Here, atmospheres, which is okay. Atmosphere is actually kind of cool. Let me throw this over here somewhere. You're over there. Okay. Pressure, right? We're gonna say is 13.5 pounds per square inch, which is gonna convert into 0.9186 atmospheres. So, a cool thing is, so 1 atmosphere is the standard pressure of the world around us. Is 1 atmosphere. So okay, cool. All right, so we have a lot of information here, right? We got the volume of football, the temperature in the locker room, and we got the pressure. This is a constant. We don't really need this. This is the amount of particles that are in the football, which we could calculate. Yeah, let's do that. We can calculate that real quick. So here, the first question we could ask is like how many molecules of oxygen are in the football. Okay, this is a if you ever wondered like how many oxygen atoms are actually in the football, this is the way you could do it. So what am I going to do with this equation? What am I going to plug in for things?
The pressure.
Good.
You would do the 0.9186.
Very good.
ATM.
Good. And then I need the volume.
Volume will be the 5,000 centimeters cubed.
So another thing I didn't say is volume needs to be in meters cubed is what it has to be in. So this is
Let's convert that.
we got to convert that. So yay, here's a little thing. This is a little. Have you done stoichiometry before, Philip?
No.
Okay.
I don't think so.
I'm going to show you how you convert how many meters cubed is equal to 5,000 centimeters cubed. Okay. So what you do, it's a thing called stoichiometry, which is a cool way to convert units. And so what you do is these are called conversion factors, and we're just going to multiply by converting between different things. So I want to get to meters, but I have centimeters. What's something you know about centimeters and meters? A relationship between them.
They're easily divisible, I think.
Yeah. How many centimeters are in a meter?
I don't know. Wait. Centimeters in a meter?
Yeah. How many centimeters in a meter?
500 or 100?
They're 100. Good. 100.
100.
So I'm going to put 100 centimeters on the bottom here. I'm going to put 1 meter on the top. So do you notice that this fraction, 1 meter and 100 centimeters, this fraction is the same thing as 1 because 1 meter is 100 centimeters?
Yeah.
Right? So, and here's the rule about math and everything. You can do whatever. You can multiply this by anything as long as it is 1, and it won't change it. It won't change the actual value of it, right? So what am I going to do is this. I'm going to, okay, cool. 1 meter is 100 centimeters. 1 meter is 100 centimeters, right? See how I'm multiplying this thing a bunch of times by things that are basically just 1, which is legal. You're allowed to do that. So now what happens is if I multiply everything through the top here, right? Do you see how I'm going to get 5,000?
You're still going to get 5,000
centimeters cubed, but then this is a meter times a meter times a meter. A meter times a meter times a meter is a meter cubed, right?
A meter cubed, yeah.
Okay. And then on the bottom here, I have 100 times 100 times 100, right? So I got 100 to the third, right? Times centimeters cubed, right? Because centimeters. Now look what happens. This is going to go away because this is going to cancel with this, right? And I'm left with 500, or 5,000, sorry, over 100 cubed, which I should be able to do this in my head, but I'm lazy. That's going to be 0.005 meters cubed. So do you see that, Philip? Do you see how we converted from centimeters cubed into meters cubed?
Yeah.
Yeah.
It's how we converted like 30 other things, but yeah.
Yes. Well, yeah. This is a cool way to convert for instance, things that are like cubed and squared and whatnot. Is to you just have to do it the amount of times it is, because sometimes this could be square centimeters and I want to go to square meters, and All right, so this is 0.005. So that's a quick little intro into what stoichiometry is. That's one of the first things actually I taught when I was doing this earlier. I don't think Soar got it when I first did it. I was like, come on. But he's a little young for it. You're older. You should be able to get it. Okay, good. So I'm going to put 0.005.
Maybe
right?
I'll get it more if I take chemistry this year.
Yeah, and you will, dude. You're going to do so much stoichiometry in chemistry. Okay. Okay, so N is equal to the number of molecules, which I don't really know. Okay. R is going to be 8.314. That's just a constant you have to know. And then T.
That's the constant.
Yeah, this is what's called the ideal gas constant. Ideal gas constant.
And then T is 298.6 Kelvin.
Good, very good, nice. Yeah.
So what are we gonna do about N though?
We're gonna solve for N. We're gonna solve for N, because
that's what we're solving.
Yeah, because N is the number of molecules that are in the football is what it is.
Okay.
Yeah, right. So here we can do some math for this real quick. So 0.9186 times 0.005 divided by 8.314, and then we're also dividing by 298.6. What do we get? Ooh, we get a very, very, very small number. Let's see. Okay. What we end up getting is that N is equal to 1.85 times 10 to the minus 6. Okay? Another way to do that, this would be 0.00000 1, 2, 3, 4, 5, 6. Yeah. is what this would be. Have you guys done scientific notation either? Have you done that?
Yeah, I've done that before a bit.
Yeah. It's just a faster way to write this. Yeah. So, and this unit, the unit for N, this is equal to moles. Have you ever seen that before, moles? Probably not, right? Moles is yeah. So here, moles is just a unit. This is just another unit. So what we say is that 1 mole, this is called Avogadro's number, is technically what they call it. Avogadro. It sounds like avocado number. 1 mole is equal to 6.02 times 10 to the 23. So this is a big fucking number, right? Because it's got 23 zeros after it. Let's see. Okay, and so it's that many moles, and what we say is that 1 mole of an atom is 6.02 times 10 to the 23rd individual particles of that atom. So if you multiply this by 6.02 e to the 23, this is what you end up getting. You get this is equal to 1.11 times 10 to the 18th particles. Okay? So that's a lot of particles, right, Philip? Like 10 to the 18th. That's why there's a lot of fucking oxygen. Lot of oxygen particles in this football. So cool. We solved for this, right? We got this, and actually we're gonna want to just keep this in moles because that's the unit we have to use for this. Okay, so here's a good question you can ask. We can ask the question. Okay, what is the new pressure of the football if Tom Brady goes outside and it is they play the Super Bowl in what, like February, right?
No, this was before the Super Bowl.
Oh wait, when was Deflategate?
It was
during the
It was
playoffs?
against the Colts, like during the playoffs. Yeah.
Okay. Was it in Boston? Do you remember?
No, no.
Deflategate
I'm not a
game.
football guy.
Yeah. Okay. Here it is. Deflategate. It was
It was like
against.
54 outside or something.
It was 54 degrees. You think? Okay, cool. That's yeah. Here, temperature. I can just look it up. Oh, and then someone says the wind chill, dude. Stop, dude. There's no wind chill. Okay. Let's say it's 54 degrees. Let's say they're playing a really cold game. Let's say it's 45 degrees Fahrenheit. Okay, which we would need to convert into Celsius and then into. So this is going to be 7.2 degrees Celsius, which is going to equal how much Kelvin is that going to be? 7.2 degrees Celsius.
Can you go back to the formula?
Yep, let's do it. Oh, it was right here.
So Kelvin's 273.
Uh-huh.
And how much Celsius was it? Like 7.3?
7.3, I think.
So that's going to be 300.3.
No.
No. Whoa.
Yeah, whoa.
280.3.
Good. 280.3, yeah. So this is 280.3 Kelvin is what it is, okay? All right, so we're going to use our PV equals nRT equation, right, for the gas. So this is, the pressure is what we're going to figure out, right? We don't know what the new pressure is, right? The volume is going to stay the same because the football, like, I know it's kind of shrinking and whatnot, but the actual container is not changing. Like, the amount of volume in it doesn't change. It's going to get a little bit more limp. That's why the pressure is going to go down, but it's still the same amount of volume. The container that the air is in is not changing in capacity. That's why the volume stays the same. N we figured out was, what was it? 1.85 times 10 to the minus 6. And then R was 8.314. and then the temperature was 280.3, right? Do you see how we can use this to figure out what the new pressure is going to be?
Yeah.
Yeah, right? It's kind of cool. So let's see. So 1.85 e to the minus 6 times 8.314 times 280.3 divided by 0.005. Ooh, okay. So we get a new pressure. Fly here is equal to 0.86 atmospheres. Okay. So do you see how the ball started at 0.9186 atmospheres?
Yeah.
And now, since the temperature drop has happened, it's at 0.86 atmospheres. So let's convert what that is into a PSI, right? To see if the ball would still be within regulation, right? So let's.
Now you need to let me know what the conversion is for this one.
Yeah. So I okay. So the conversion. Do I know what the conversion is? I don't actually. I know it to kilopascals and I know it to millimeters of mercury, but I don't know it. I don't know it to pounds per square inch. This is what engineering people do. Engineering people know all these ones because like they know how to always go from inches to metric and whatnot. Let's go from atmosphere to PSI. Okay, cool. Here we go. This is equal to 12.67 PSI. Right? So.
And what are the regulations?
Yeah, what were the regulations for a football again? Let's.
12.5 to 13.5.
Ah, see? So do you see how the temperature change would not be able to knock it outside of the regulation?
Yeah.
Right? So this is why Tom Brady's argument of like, oh, it was the wind, it was the temperature is bullshit. Because you can do the science on it and be like, well, wait a minute. If they had it pressurized to the maximum that it should have been, right? 13.5 inside the locker room. Even with it getting cold, even if with it getting down to 45 degrees, right? It's pretty fucking cold to play football in. It would still be within regulation. So, because I think they ended up, let's see, I had this pulled up. Like they had the pressures of the balls. Let's see what they had. Yeah. Wow. Yeah. No, dude. It was as low as 10.9 at one point, dude. Okay.
Wow.
Yo, yeah. Look at Let's pull this up. The Patriots, dude, they're fucking cheaters, dog.
I mean, 12.5. What if they put it to the absolute low?
Oh, you mean what if they started at 12.5?
Because you don't have to put it at 13.
You don't. Yeah. Well, you're expected. And again, it's not like you have to put it in. Where's this? Not pasting. Come on, girl. No. But okay, no. You bring up a good point. Like, what would happen if for instance, they had it at the what was the absolute lowest again?
12.5.
12.5.
Oh wow.
Yeah, if they do it at the lowest, then of course it would drop down a little bit, right? Because this dropped down from 13.5, right, to 12.6.
13.5. 12.67.
Okay, so you can actually figure out how much it would drop if it was starting at 12.5. Okay, because whatever the drop is in terms of temperature, it's proportional. So for instance, whatever percentage this dropped.
0.83.
So this dropped 1.83. So it dropped 1.83 divided by 13. You have to get a percent change, is what you have to say. Which I can explain that next lesson or something. But yeah, so 1.83 divided by 13.5. So it's going to drop 13.6%. So this is what we say is a 13.6% drop. Okay. So now I can calculate what 13.6 of this would be and what that drop would be, right? So 13.6, which is 0.136 times 12.5. So that's a 1.7 drop. Okay. Which, okay, would be 10.8. Would be 10.8. Yeah, you're right. So this would drop to 10.8, which, okay, is not, right, that's not totally ridiculous, because let's see. Let's here. These were the scores for This was the Deflategate stuff that happened. So these are what the scores were. The scores. These are what the temperatures were. The pressures were measured on the ball during the Deflategate. So 10.8, right? If they put it to the bare minimum in the locker room, right?
Yeah.
10.8 would show up, right? I think in general, I think in football, correct me if wrong, I'm not really a big football guy, but I think they just say, like, we need to make sure that that it's the proper temperature once it gets outside. And you can see, obviously, the Patriots didn't give a fuck, dude. Like, they were having it like 10.5, whereas the Colts, right, had theirs at 12.7 and 12.5, right? Much higher. So, I mean, there's definitely something fishy about this. Anyways, yes, cool, awesome. Yeah, that was a great question there, Philip. I love when we can apply math and science to like real world shit. Isn't that kind of cool? Here, I'm gonna add you get a bond coin just for asking that question. Nice. I'm home this Monday or Tuesday. Okay, awesome. Welcome. Thank you everyone for attending office hours and whatnot. Now what we're gonna do is some Jackbox trivia games. Yeah, he's like, yeah, dude. Now we can have fun, dude. Fuck this math and learning stuff. Now we get to have fun. Shut up, right. T-Bone. Okay, here. So let me pull that up for you guys.
He hurt my feelings, man.
He hurt my feelings.
I'm gonna be with my parents.
My feels